So good afternoon, everybody. My name is Pedranz from the University of Trento, and today I'm going to present you some finite element modeling investigations about the yield locus of this particular ductile cast iron. So in a previous work, some biaxial tests, so basically axial plus torsional tests under string control were carried out on tubular cast iron specimens, as you can see here. Different biaxial loading combination were investigated. As you can see here, the angle means different combinations of axial and shear loading. And Walter-Baye multi-action machine was used. It was discovered that the yield locus of this cast iron deviates from the von Mises criterion. So basically, as you can see here in these two graphs, as long as biaxial loading is imposed, the yield strength of the material is higher than that predicted by von Mises. As you can see here, it assumes a cusp-like shape that was found to be well fitted by the criterion proposed by Camano, which is a criterion for composite materials, basically. So also a tension compression asymmetry can be observed, but this was already well known from literature. So we decided to investigate this strange behavior by finite elements modeling. So first of all, we generated a three-dimensional model by means of a Python script according to the experimental collected data, which are the graphite fraction, mean nearest neighbor distance, and the nodules, graphite nodules diameter. These data were collected by computed tomography scans and classical optical metallography. So the graphite nodules were modeled as spheres with different dimensions, while the matrix was modeled as a bilinear kinematic steel, so with elastic modulus of 210 gigapascal. Then initially we performed the simulation under axial tensile loading, as you can see in these pictures, and we tuned the elastic plastic properties of the matrix according to the experimental curves that are represented here in red. So we set basically the yield strength and the plastic modulus for the material. Then we carried out other simulation with the 3D model under different biaxial loadings. However, these simulations are very, very computationally costly. So we decided to try to use another approach with two-dimensional domains in order to collect more reliable results and do a little bit of statistics also. So we generated 50 different domains with dimensions 2 times 2 millimeters, and the nodules arrangement is set again according to the experimental data. We modeled the matrix as bilinear kinematic material. We exploited plane 183 elements from the ANSYS library, so they are quadratic elements under plane stress behavior. Because we changed from 3D to 2D model, we had to tune again the matrix. So we tuned it again, always according to the actual experimental curves. So we tuned the yield strength and the plastic modulus. And then we carried out several biaxial loading simulations. Here we show the axial and the pure shear loading conditions. And as you can see, we are able to report results with a scatter band. So these are the results collected with 50 different different domains, and the matrix properties were kept fixed. So as you can see, the predictions are pretty accurate, but however, we were not able to predict the tension compression asymmetry, which is typical for ductile cast iron. So we hypothesized that as long as the actual component is compressive, the graphite nodules are able to make a real difference in the yield strength of the material. So we decided to model them as compressible fluids, exploiting the elements 241 from ANSYS. And we had to tune the bulk modulus of the material, and we did it according to the pure axial compressive experimental curves. So we found a value of 750 gigapascal. And at the end, we carried out different several biaxial loading combinations simulations. These are the results, basically. So as you can see, our models were able to well predict the experimental collected data. The red ones are the two-dimensional simulations. The left part of this graph represents the biaxial conditions where the axial loading becomes compressive. So here we exploited compressible fluids for the graphite nodules, and here we modeled them as voids. We report also the three-dimensional results. So in the future, we are planning to try to fit the curve with other three-dimensional simulations. And we want to analyze the results more in depth in order to fully understand the microscopic behavior of this material, and try to find a correlation between the two-dimensional and three-dimensional models in order to find a sort of factor to switch. I finished. So thank you for your attention.